Hi class, so this is our second to last lecture on acids and bases. And this lecture is going to be on section 14.6. It has to do with buffers. So we're going to talk about buffers. The worksheet we're going to do is worksheet 18. So you might want to have that handy. This is a problem solving worksheet to calculate the pH of buffer solutions. So let's get started. I'm going to share my screen. I have a PowerPoint here as usual. It's a little bit longer than normal. It's got 15 slides, but I think we'll go through them pretty fast. So chapter 14.6 on buffers. What we're going to learn in this section is understand what a buffer does and how to make a buffer. So those are the first two things we're going to cover. What does a buffer do and how to make it? It's we're going to be these are aqueous solutions. So those are the kind of buffers we're going to study in this chapter. We're going to understand how a buffer works and what buffer capacity means. And then we're going to apply equilibrium calculation to buffer solutions when an acid or a base is added to the buffer. So what is a buffer? It's a solution that resists major changes in pH when a small amount of acid or a base is added to it. And so these are made up of, let's see, it contains a substance that will react with and remove an added base. It also contains a substance that will react with and remove an added acid. So what kind of a substance is that? Well, it's a weak acid and its conjugate base. That's what we've been learning about all along. Acids and their conjugate bases, or bases and their conjugate acids. So it doesn't necessarily have to be a weak acid and its conjugate base. It can be a base and its conjugate acid. So here's how a buffer works. So in this slide, on the left side is well, we have two solutions at pH 8. That's obvious. The one on the left is not buffered, or one is labeled not buffered, one is labeled buffered. So what happens when we add 0.1 molar acid, say 1 mil of 0.1 molar acid to each of those? Well, the one that's not buffered, the pH changes to 4. The one that is buffered, the pH stays at 8. In these solutions, we had a pH indicator. So when the pH changed to 4, the solution turned red. If you remember the PowerPoint where I had a demonstration of a pH indicator that changes color, the purple cabbage lettuce pH indicator that changes color at different pHs. So here's another demonstration of a buffer. So if we have a buffer at pH 7, if we add some acid to it, the pH may go down just very slightly to pH 6.9, perhaps. You add a little base, the pH might go up. It is going to go up, but it's not going to go up very much. It'll go up from 7 to 7.1. So what happens? A buffer solution maintains the pH by neutralizing small amounts of added acid or base. So an acid must be present to react with any added base, for example, hydroxide. That's where the acid comes in your buffer. And a base must be present to react with any added acid, which is hydronium ion. The base is the conjugate base of the acid. Now, not any acid and conjugate base work. There have to be a weak acid and salt if it's conjugate base. So here's a combination that would make a buffer. So we have acetic acid and sodium acetate. Acetic acid is here. AQ, understanding that these are aqueous solutions. of acetic acid. And the conjugate base is here. It's the acetate ion. Remember, ions don't exist by themselves, so we have to add a salt that contains acetate. It could be sodium acetate, ammonium acetate, maybe not ammonium acetate because ammonium ion is acidic. Maybe potassium acetate, magnesium acetate, any of those would work to provide the conjugate base of acetic acid. The best buffer is made when there are equal concentrations of acid and its conjugate base. But that's not necessary. The buffer that controls our pH in our blood is a carbonic acid bicarbonate buffer. And in that case, the bicarbonate is at a much higher concentration of carbonic acid, and the pH is controlled at around 7.4. So here's what an equation, a buffer equation might look like. So we have an acid in water producing this conjugate base. So when you combine an acid and its conjugate base, you produce a buffer solution. So this is what the equilibrium would look like. Similar equilibrium with a base and its conjugate acid could also be used to make a buffer. And the examples we're going to talk about in this lecture, we're going to just talk about acids and the conjugate bases, but that's not required. You could also have a base and a conjugate acid. Usually a base and a conjugate acid buffer would be a buffer that you'd set up for a higher pH. So how do buffers work? In the example, buffer with acetic acid and the sodium acetate, the salt dissociates to produce the acetate ions and sodium ion in water. The sodium ion is a spectator ion, so it's not involved in this equilibrium. So the salt would provide the higher concentration of the conjugate base than you'd normally get in the equilibrium with acetic acid alone. So remember, we did a calculation previously where the concentration of the conjugate base was very small because the Ka of acetic acid is very small. The Ka, remember, I'll just write this. This is a acid we've seen previously. The Ka was 1.8 times 10 to the minus 5. So that means that there's not very much acetate ion. So acetic acid alone doesn't make a very good buffer. You have to have a conjugate base in there to soak up any added acid. So remember, buffers are designed to prevent the change in pH when either an acid or a base is added. So the acid, in this case, is acetic acid in this buffer, and the conjugate base is acetate ion. So when a small amount of base is added to this buffer, the added base is neutralized by the acetic acid. And here's the acetic acid over here. So the concentration of the acetic acid is going to go down. And the concentration of the acetate anion, or the conjugate base, is going to go up. So this is the reaction that takes place when you add base. So the acid soaks up any added base. Now this reaction is a reaction that goes through, so a strong base plus an acid completely changes an equivalent amount of acid into acetate anion. So for example, if you added 0.01 moles of hydroxide ion, that 0.01 moles of hydroxide ion is going to produce 0.01 moles of acetate ion, and in turn, you're going to lose 0.01 moles of acetic acid. It's 100%. It's the first thing you do. If you do a calculation, the first thing you do is calculate how much acid turns into conjugate base when you've added some base. And so that's how it works. When a small amount of acid is added, the reverse happens. The acid will react with the base, the conjugate base. So here we have acid, we have base. Conjugate base is going to go down. In turn, the acid will increase, not the added acid, the weak acid that's in the equilibrium. So the conjugate base of the weak acid is going to go down when added acid is put into the solution, and the weak acid concentration will go up. And so this will be the initial situation, or this is the concentration of the acid in the base, the weak acid and its conjugate base in the buffer. When you add acid, the conjugate base goes down because the acid reacts to the base, and the weak acid concentration goes up. So again, this is instantaneous and happens 100%. We did this calculation on the previous worksheet. If you recall, it was the last calculation we did. I think it was number 4 on worksheet 17. So what is buffer capacity? Well, it's the amount of an acid or base that can be added before the pH changes significantly. So it's determined by the amounts of acid and conjugate base present in the buffer solution. That is, the more concentrated the acid and conjugate base, the greater the buffer capacity. So here's a graph that shows how that works. In the first plot on the left side is distilled water. So in this graph, we have the pH of the solution. And in the case of distilled water, the pH is 7. If you add 1 drop of sodium hydroxide, the pH just shoots up really high. That's what would happen to an unbuffered solution. But it doesn't have to be distilled water. It can be a solution of sodium chloride. So there are lots of salts that don't provide any buffering capacity. And if you added an acid or a base, if you added the base, the pH would shoot up. If you added an acid, the pH would shoot down just as radically. So in the next curve, we have a weak buffer solution, a 0.01 molar buffer. And you can see that as you add sodium hydroxide, the buffer pH doesn't change too much. You know, it starts off at about 4.7. That sounds like a acetic acid sodium acetate buffer solution. And it goes up a little bit as you add base because, of course, you add hydroxide ion, you expect the pH to go up. But it doesn't go up very fast until you used up all of the acetic acid or the acid, the weak acid in the buffer. And when that's done, you've exceeded the buffer capacity and whoa, the pH shoots right up. It shoots up with just by adding 1 drop. It radically changes. But if we increase the concentration of the buffer from 0.01 molar to 0.025 molar, you can see that it takes a lot more base. You have to add a lot more base. Maybe instead of only 8 mils or 6 or 7 mils before it starts shooting up, you can add up to 20 mils of base before the buffer capacity is exhausted and the pH starts going up. In these other curves, there's 3 other curves here, even at higher concentrations of buffer, 0.05 molar, 0.1 molar, and 1 molar. And in these cases, as we added the sodium hydroxide, the buffer capacity was never exceeded. So in these higher concentrations of buffer, the pH stayed pretty constant, all the way up to 40 mils of added sodium hydroxide. That's pretty good. So that's what That's what buffer capacity means, and that's what buffer capacity does. In our blood has a high enough concentration of carbonic acid, bicarbonate, to provide a pretty constant pH between 7.2 and 7.4. With all of the metabolism going on in our bodies and in our cells. You can exceed that though. And when you exceed that buffer capacity and it goes beyond that pH range in your blood, you'll get sick, start feeling pretty bad. Okay, so what about, how do you choose an acid conjugate base pair? We've been talking about acetic acid and acetylene, but that's not the only one. There are lots of, there's hundreds, if not thousands, of weak acids in conjugate base pairs. So the choice depends on what pH, on the pH range that you want to control. And the AH equation, the Henderson-Hasselbalch equation, we're going to learn about that in the next slide. It's a little early. Anyway, it shows that pH is equal to pKa in equal molar solution. So if you have an equal molar solution of conjugate acid, of acid and conjugate base, the pH equals a pKa. So here's a and the conjugate bases and the Ka's for those. So on the left side, we have acid conjugate base combinations that would control the pH in the acidic range. Oops. There we go. So in the acidic range, so the acidic range in this case is 6.91 down to 4.74. We could go lower. So this is just a sampling. So for example, here's carbonic acid bicarbonate. That would control the pH at pH of about 6.37. That's a little lower than blood. So what happens is in our blood, the bicarbonate is a little higher. It's a little more base in the buffer, which raises this pH up above, just above 7. Here's, let's see, I think here's acetic acid and acetylene. That's a buffer that would control the pH at 4.75. This is citric acid and citrate anion. No, this is a citrate anion, and this would be the maybe bicitrate anion or something. So this is interesting. This is an interesting combination. So this acid, H2C6H5O7 minus, is an ion, is an acidic ion. It can lose a hydrogen ion to produce HC6H5O7. It's derived from citric acid, which has 3 acidic hydrogens. For this acidity, the pK is 1.8 times 10 to the minus 5. It's almost the same as acetic acid. Gives you a pKa of 4.74, which would be equal to the pH that the buffer would control. So this substance, if you remember, we call it because it could act, the H2C6H5O7 could act as an acid or a base. So amphiprotic substances can be used to make buffers also because they have conjugate, they act as an acid with a conjugate base. On the right side of this slide, we have some acids that have a little bit, the weaker acids. Remember, the stronger acids have a higher pKa. These have a lower pKa, and they would be used to control the pH in the alkaline or the base region, so above pH 7. You can see here we have combinations. This would be bromous acid. No, maybe hypobromous acid, HPRO. And here's the hypobromate anion. And that would be used to have a buffer at pH 8.7. So we're going to learn, I'm going to show you, we have equation, this HH equation shows that the pH is equal to pKa if you have equal concentrations of acid and conjugate base. So here's some other conjugate acid base pairs. You can use a phosphate anion. There's a different phosphate anions produce different buffers at different pHs. There's bicarbonate and carbonate. There's phosphate, hydrogen phosphate, dihydrogen phosphate, ammonium and ammonia. So these are other combinations of acids and conjugate bases that could be used. So just in summary, the pH of the buffer solution will depend on the conjugate acid base pair chosen. And we can calculate that using the HH equation. So what is this HH equation? HH stands for the Henderson-Hasselbalch equation. These are two chemists that studied pH in biological systems in the early 1900s. Tell us about them. So it's derived from our equilibrium expression for acids. So K equals H plus times A minus over HA. So if you take the logarithm of both sides, you get the log of K equals the log 10 times H plus times A minus over HA. You can break this out to log of H plus the log base 10 A minus over HA. Well, the pKa, remember the P transformation of a number is minus the log. So the log 10 Ka is equal to minus pKa. So we have minus pK equals minus pH plus the log of the concentration of the conjugate base over the acid. And we can arrange that so that we get this Henderson-Hasselbalch equation at the end. This is the equation at the bottom. pH equals pKa plus log base 10 A minus over HA. Note the problems number 2 and 4 in worksheet 817 could have been solved using this Henderson-Hasselbalch equation. We solved it using ice tables, and the only thing you have to worry about using the Henderson-Hasselbalch equation is that small x assumption that we made to simplify the calculation from the ice table so that we didn't have to use a quadratic equation applies. So that small x approximation where we can reflect the change in concentration that goes on, that has to apply to use this equation. So that's it. Let's see, I have a little note here that says we have to go on to worksheet 18. So I'm going to go on to worksheet 18. And turn on the camera, get worksheet 18 here. Come on. Sometimes I click that mouse too fast. And I turn things on and off before the computer reacts. So here we go. Here's worksheet 18. Let's see, I'll turn on the light. I don't think we need a light. It looks pretty good. Okay, so let me just line it up here. So I'll zoom in here. So the top of this worksheet explains buffer solutions. So I'll let you read that on your own. And we'll look, let's go directly to the problem. There's only 2 problems on this worksheet. So the first problem says calculate the pH of a solution made by adding 15.01 grams of acetic acid and 20.51 grams of sodium acetate. This seems to be our favorite buffer, or favorite weak acid and conjugate base to look at. We've been studying, doing calculations with acetic acid and sodium acetate for several lectures now. Anyway, we're going to add enough water to this to make a 550 ml solution. So this doesn't tell you what the molar concentrations are. So the first thing we have to do is figure out what is the molar concentration of acetic acid, what is the molar concentration of sodium acetate. So we need to calculate the molarities of those two things. So that's the first step. We're going to use the Henderson-Hasselbalch equation to solve this. So I wrote the equation here. This is the equation for you to write down. You'll need to use this probably on the exam, and I'm sure on your homework. So first, let's calculate the molarity of the acetic acid. You have to know the molecular weight. So I figured out the molecular weight. It's 60.06 grams per mole. If you look it up, I just added up the atomic masses of these elements in the formula. If you look it up on the internet, it's a little bit different from that, 60.05. And that changes the answer slightly. Well, so if you use 60.05 instead of 60.06, you'll get a very slightly different numbers. But this is how I did the problem. So we'll use 60.06. So 15.01 grams of acetic acid divided by the molar mass gives you 0.2499 moles. You divide that by the total volume, 550 mLs. This has to be changed into liters, right? To calculate the molarity. The molarity is moles per liter. And so we change the 550 mLs into 0.550 liters. And that gives us a molarity of 0.454 molar. I'm going to move this over a little bit so you can see that. Maybe I'll zoom out just a bit, just a little bit. Okay. Okay, so that's the molarity of the acetic acid. Step 2, we need to calculate the molarity of the sodium acetate. Well, that's pretty much the same. There's a few things we have to add up first, like find the molar mass of sodium acetate. That turns out to be 82.04 grams per mole. And then we'll take our 20.51 grams of sodium acetate, divide it by 82.04 grams per mole. When we do this, if you remember our unit cancellation method for doing these calculations, our grams cancel. We're left with moles. Divide the moles by our volume, which is 0.550 liters. We'll get the concentration of the sodium acetate, which is this is concentration of the acetate ion also. So the concentration in solution of the acetate ion is 0.455 molar. The spectator ion in sodium, that's the concentration of the sodium also. So when we do this calculation, we get the concentration of the sodium ion and the acetate ion. But the sodium ion doesn't matter. It's there, but it's not influencing the chemistry. So if you remember when you wrote net ionic equations in your previous chemistry class, we call sodium ion a spectator ion. So the first step, now that we have the concentrations, we can use our Henderson-Hasselbalch equation. So, but to do that, we need to calculate the pKa. So we know the Ka for acetic acid is 1.8 times 10 to the minus 5. Take the minus the log of that, we get the pKa of 4.745. So now we have all the values we need to plug into the Henderson-Hasselbalch equation. We have the pKa 4.745 plus the log of the acetate ion, the conjugate base, 0.455, divided by the concentration of the acid, 0.454. When you do this calculation, what I usually do is I'll figure the log number first, and I'll add it to the 4.745, whatever works, and you get 4.75. Now this particular calculation is pretty easy to do because this is close to 1. The log of 1 is 0, so this is close to 0. This particular calculation turns out to be 0.001. So the we add 0.001 to 745, we get 746, which again rounds to 4.75. So I think this problem was set up so that this turned out to be the log of 1, but because of my little bit different molar mass up there for acetic acid, they didn't come out exactly the same, but pretty close. So when you use equal concentrations of the acid and the conjugate base, if the concentrations are equal, this log of 1 disappears. So the pH equals the pKa. So previously, when I showed you the previous slides, that you design a buffer for the pH based on what the pKa is of the acid, based on what the acid equilibrium constant is. Because of this, if these weren't equal, then you'd get a different pH for the buffer. So that's what this says at the bottom of my worksheet. If there are equal molar amounts of the acid and the conjugate base to make the buffer, then the pKa equals the pH. All right, let's go to the second problem. The second problem has to do with what happens if we add a strong acid to this buffer. So what we think is going to happen is that the pH is not going to change very much, but we can calculate that. So we want to calculate the pH of the solution if 6 mils of 1 molar HCl is added to the above solution. Now, our solution is 550 mils, but the molarity of the weak acid and the weak base, remember, was only about 0.475. We're adding 6 mils of 1 molar HCl. That's quite a bit of acid. The concentration of the acid is 1 molar, which is more than twice as strong as the concentration of the acetic acid and sodium acetate. So let's see what happens. So the reaction that's going to happen initially when you add the HCl, we said added acid is going to react with the conjugate base to make weak acid. That's going to happen completely. So we need to calculate, first thing we need to do is calculate the loss of acetate ion and the gain of acetic acid before using the Henderson-Hasselbalch equation. And when these changes occur, the concentrations are going to change. So we have to recalculate the concentrations of acetic acid and acetate anion. So first of all, to know how the added HCl is going to affect it, we have to know how many moles are added. So we have 6 mils converted to 0.006 liters times a molar concentration, which is 1 mole per liter, yields 0.00600 moles of HCl are added to our buffer solution. So that's going to react with the acetate. So if we go back to our previous problem, if you look at our previous problem, we determined that our buffer had 0.2500 moles of acetate anion. So we have to subtract the moles of HCl that we calculated because it's going to use up, it's going to react with acetate anion. That leaves us 0.2440 moles of acetate anion. So we can divide that by our new volume, which is 550 mils plus 6. So we have 556 milliliters of solution now. But that 566 must be converted, milliliters must be converted to liters, and we'll calculate the new molarity of the acetate anion. Turns out to be 0.439 molar. So now we have our acetate anion concentration. Step 4, we need to calculate how much acetic acid has been produced in this reaction. So we know that originally we had about 0.2500 moles of acetic acid. We're going to add 0.006 moles because that's how much acetate anion was converted into acetic acid with the added HCl. That gives us 0.2560 moles of acetic acid. We're going to divide that by the new volume, which is 2560 moles divided by 0.566 liters equals 0.460 molar acetic acid. Let me write the formulas. HOAC here. This is OAC minus up there. So now we can plug that into the HH equation to solve for pH. So here's our pH equals pKa plus the log of AC minus acetate anion divided by the acid, 0.439 molar up here, divided by 0.460 molar. It's not 1 anymore, so we're going to have to solve it. We end up with 4.745, which is the pKa minus 0.020. That's what the log of these concentrations are. When we do that, we find out our pH is 4.73. So if you remember on the last problem, in our buffer solution, the pH was 4.75. So it changed. So when we added 6 mils of 1 molar HCl, the pH went from 7.45, oh, excuse me, 4.75, there we go, 4.75. pH went from 4.75, this kind of looks awful, to 4.73, we added HCl. So we could say that buffer really worked. It really, pH didn't really change much. We can also say we didn't exceed the buffer capacity. How would you know what is the buffer capacity? Well, the buffer capacity in the terms of acid would be equal to 0.25 moles. So we could keep adding HCl up to the point where all of the acetate anion is used up. So this buffer would be able to absorb 0.25 moles of HCl before the buffer capacity is exceeded. So that's the value that determines the buffer capacity right here for this one. This is the buffer capacity. So that's the end of the, let's see, I'll go back to the camera. So that's the end of the lecture on buffers. So that's 14.6. And we have one more lecture left in chapter 14. And so I'll be back with that pretty soon. So you guys take care. and I'll see you later.